Yes, good morning, students. Today we are going to see the subject theory of computation. The title is Context-Free Grammar. And in this, we are going to learn about the context-free grammar introduction, derivation tree, otherwise called as parse tree, sentential forms and its partial derivation tree, and the types of derivation tree, left and right recursive grammar, and then ambiguity in context-free grammar. At last, the simplification methods in context-free grammar. Let us start with this context-free grammar. First, we have to know what is grammar. So we know that grammar is set of rules which are used to check whether the given string belongs to a particular language or not. Yes. So then, what is context-free grammar? So context-free grammar is going to be a notation which is used to specify the syntax of the language. For any given language, there will be a syntax. In order to represent those syntax, I will be having a grammar which is called as context-free grammar. So which are mainly used in the design of the parser. So we'll go to the definition of the context-free grammar. So this context-free grammar, in short, you can call CFG. So CFG is a way of describing a language by recursive rules or the substitutions of rules called production rules. A CFG is denoted as a quadruples, that are four tuples, N, T, E, S, where this N is called a set of non-terminals. Capital T is set of terminals, where this T uh, should not be, that is, when we do intersection with the non-terminal and terminal, it should be equal to null. So there should not be any common symbol used in the N and T. Then the P. P is set of production rules. Okay. So which is of the form N tends to N union T. So non-terminal, union, terminal, and which is of any combinations. So the left hand side of the production rule, P does have any right context or left context. And this S is a start symbol. Okay, so otherwise instead of this N, we can also use V in order to say it as a variable. Okay, so you can represent G is equal to NTPS, or we can represent it as VTPS, where the V is nothing but the variables, or else you can represent by N, which is nothing but non-terminals. Non-terminals otherwise called as variables. Okay, so this T is set of terminals. Okay, so where this N and T are final set of variables and terminals, we assume that this N and T are disjoints there. Okay, so that is this N intersection T is equal to null. And P is finite set of production rules. So each production is of the form A tends to alpha, where this A is variable or the non-terminal, and alpha is the strings of symbols from this N union TD whole star. Finally, the S is a special variable called start of the start symbol. Okay, so here we have some examples. So here you can see the four tuples A, A comma B comma C, P and A. So here set of non-terminal is A. Set of terminals are A, B, C. And set of production rule P. Here you have only one uh, variable, which is A, and that is going to be the start symbol. And here the production rules are described. A tends to small a capital A, or A tends to small a b c. So this is one production rule. This is one example for CFG. And the next example, uh, set of uh, set of symbols. So yes, then A comma B, then P, then S. So here S is a start symbol. So here the production rules are S tends to ASA, S tends to BSB, S tends to epsilon. And then another example for the CFG, set of non-terminals S, F, and set of terminals 0, 1, and then set of production rules T, and the start symbol S, where the production rules are given as S tends to 00 S, or 11 F, or F tends to 00 F, or epsilon. So this, you know that the context-free language are generated from the grammar called context-free grammar. And this grammar contains 4 tuples, the quadruples, N, T, P, S, where this N is set of non-terminals, T is set of terminals, and this N and T are disjoint set. That is what we can represent. N intersection T is equal to null, and P is set of production rules, and it should be of the form always at the right hand side of the production you will be having the combinations of non-terminals and terminals. At the left hand side you will be having only one non-terminal. So this is the rule, okay, in order to represent the production rule for CFG, context free grammar. And S is the start symbol, and we have seen some examples for CFG. Clear? Okay, let us move to the next topic, derivation tree, otherwise called as parse tree. Okay. So before moving to this derivation tree, we have to know the derivation. Okay. So a grammar is used to describe a language by generating each string of that language in some manner. Okay. So then, what is meant by derivation? See, suppose if you have a production rule, A tends to beta, okay, and which belongs to a grammar G, and alpha, gamma are any two strings on this terminals and non-terminals. Then we say that the alpha, capital A, gamma directly derives alpha, beta, gamma in G. So the generation of derivation tree. So derivation tree or the parse tree is an ordered rooted tree that graphically represents the semantic information, a string derived from a context-free grammar. Okay, so we can able to derive set of strings from the context-free grammar. So for that, in order to represent that derivation into a graphical representation, we can use a tree called derivation tree or a parse tree. So derivation tree or a parse tree is an ordered rooted tree that graphically represents the semantic information, a string derived from a context-free grammar. So there are some representation techniques. So root vertex, so must be labeled by start symbol. Always we have to use a root node of the tree which must start with a start symbol. And the vertex labeled by non-terminals. And the leaves labeled by the terminals, are sometimes you may get epsilon. Okay, so this is how you have to generate a derivation tree. So always the root of the derivation tree must have the label start symbol. Other vertices are labeled by the non-terminal, any of the non-terminal, and always the leaf node must contain only the terminal symbol or epsilon. Epsilon is empty string. So if you have a production rule, S tends to x1, x2, and so on, xn. Okay, then the parse tree or derivation tree will look like this. Look at here. So S is the start symbol, and which has a production rule x1, x2, and so on, xn. So we need to create a node with the label x1, x2, and so on, xn, which are connected to the root node, yes. So this is how we can able to draw a derivation tree or parse tree. So there are two different approaches to draw a derivation tree. So top-down approach or bottom-up approach. See, always the top-down approach starts with the start symbol S, goes down to the tree levels using the production. So starts with the start symbol, then the start symbol can be replaced by the right hand side of the production rules. And then what we can do, we can choose any one of the non-terminal and we can grow the tree by replacing the non-terminal by its production rules. So this approach is called as top-down approach. And we have another approach which is bottom-up approach. So starts from the tree leaves, the strings, and we can combine some set of strings and we can replace it by any of the non-terminal and we can end the tree with the start symbol. Okay, so which can proceed upwards to the root, which is the starting symbol. Yes, so there are two approaches to draw the derivation tree. One is top down approach, starting from the start label to the set of strings, and another is the bottom up approach. We can start from the tree leaves, the terminal symbols, and we can proceed upward to the root, which is the starting of the tree, the root of the tree. Okay. So derivation or yield of the tree. So what is a derivation or yield of the parse tree or the derivation tree? Is nothing but the final string obtained by concatenating the labels of the leaves from the left to right. It's very important. See, we can generate a set of string from any grammar and which can be represented as a tree. See, always the tree node starts with the start symbol, and the tree has some leaves. So that leaves are nothing but it's going to have some terminal symbol. So in order to get the derivation or the yield of that parse tree, what you have to do, you have to read the leaf node from left to right. Okay, so the derivation or the yield of the parse tree is a final string obtained by concatenating the labels of the leaves of the tree from left to right, ignoring the nulls. We need to ignore the nulls because null is an empty string. However, if all the leaves are null, the derivation is called null. Okay, we'll see one example for that. See, let C of G. Okay, you know that C of G will have 4 tuples: set of non-terminals, set of terminals, set of production rules, and a start symbol. Okay. So N, capital N is set of non-terminals. So set of non-terminals, otherwise called as variables. So here, suppose you have S and T. T is set of terminals. So A comma B. So start symbol is here you have only one non-terminal which is going to be the start symbol, and there are some production rules are given. So S tends to S is R, S tends to SB or epsilon. Okay, and suppose if you want to derive a string AB, AA, BB from the given grammar, so how can you derive the string AB, AA, BB? So always you need to start with this S. S is the start symbol. So this S can be replaced by SS or ASB. So suppose you are taking SS. Then what you are supposed to do, you can replace this first S by any of its production rule. Suppose you are replacing it by ASB. Okay. So then what you can do, you can replace this S by epsilon. So the resulting sentential form as ABS. Then you can replace this capital S by ASB. Again, you can replace this S by AB. That is ASB. At last, you can replace this S by epsilon. So the final string which you obtained is ABAABB, which is required to derive from the given grammar. So now what you are going to do, you are going to generate the derivation tree for our parse tree for the for this derivation. So first S is replaced by SS. So we have to draw two more nodes as a child node for this S. Then this S is replaced by ASB. Then this S is replaced by epsilon. Then this S is replaced by ASB. Then this S is replaced by ASB. At last this S is replaced by epsilon. So look at here. So always the start node must be in the root. Yes, there the root node is the start symbol, labeled as a start symbol. And if you look at the leaf nodes, so A, epsilon, B, A, epsilon, BB, which are nothing but the terminals. We know that leaf nodes may be labeled with the terminals or epsilon. Yes. So can you able to understand what is derivation tree or the parse tree? Yes. We'll see the next thing. Okay, next is sentential form and a partial derivation tree. So a partial derivation tree is a subtree of the derivation tree or the parse tree, such that either all of its children are in the subtree or none of them are in the subtree. Okay, if any CFG of the productions are S tends to AB, A tends to AAA or epsilon, B tends to BB or epsilon, the partial derivation tree can be the following. So look at here. So we have started with this S, and this S can be replaced with AB. So AB is the only option you have for S. Okay. This is called as sentential form, or if you draw a tree for that, which is called as partial derivation. Okay, if a partial derivation tree contains a root S, it is called a sentential form. The subtree is a sentential form. Okay, so if you take a partial tree and which has a root, then it is called sentential form. Okay, then see, previously we have seen there are two approaches. One is top-down approach, another is bottom approach. So here there are two types of derivation. Leftmost derivation, rightmost derivation. Okay. So in order to derive a string, if we replace the leftmost non-terminal by its any of the production rule to generate a string, then it is called as leftmost derivation. So leftmost derivation is obtained by applying production to the leftmost variable in each step. If you choose leftmost non-terminal and if you replace that non-terminal by any one of its production rule in order to generate a required string. So that approach is called leftmost derivation. So in the derivation, if you choose a rightmost non-terminal to derive any string, then that is called as rightmost derivation. Clear? Okay, we'll see one example for that. So let any set of production rule in CFG be x tends to x plus x or x into x or a. So over an alphabet A. So here the alphabet is A, but when you want to list out the capital T, that is set of terminals, so plus int A, all will come together. So suppose if you want to find out leftmost derivation for the string A plus A into A, then how can you do? First we have to start with this x tends to x plus x. Okay. Then, so look at here, there are two non-terminals, the first x and the next x. But if you choose the first x to replace by any one of its production rule, then it is called as leftmost derivation. So you need to choose the first x, then you need to replace it by any one of its production rules. Say for example, you are taking A. Then you have only one non-terminal x. So that can be replaced by its production rule x. star x. Then here you have two non-terminals. So here, if it is a leftmost derivation, you need to choose the leftmost non-terminal x. So here, this x is replaced by a. Clear? Then you have only one non-terminal x that you can replace by a. So at last you have arrived at the string a plus a star a. But in order to derive it, we have chosen a leftmost non-terminal and we have replaced the leftmost non-terminal by any one of its reduction rule. So this is called as leftmost derivation. And here you can see the corresponding derivation tree, the parse tree. So first step, we have taken x tends to x plus x. So x tends to x plus x. Then the leftmost x is replaced by a. And the next step, we had only one x, only one non-terminal. So we can choose that to replace, and that x is replaced by x into x. So now there are two non-terminals. So you need to choose the leftmost non-terminal x, replace it by a. Next we have only one that can be replaced by a. So the intended string we are required to derive is a plus a star a. So we can stop the derivation here. Look at here, all the leaf nodes are the terminals. Other than the leaf, all other nodes or non-terminals are the variables, and always the start node, that is a root node, contains a start symbol. So next we'll see the rightmost derivation for the same string a plus a star a. Okay. So with the rightmost derivation, you are supposed to choose a production x into x star x. Okay. And here you are supposed to replace this x by a. So rightmost non-terminal, you need to choose to replace. Yes, this x, the rightmost x is replaced with a. Then you have only one non-terminal. So this non-terminal can be replaced by the production rule x plus x. So here you have two non-terminals. So choose the right one. So right side x is chosen and which is replaced by a. Again you have only one that can be replaced with a. The corresponding derivation tree are the parse tree. Look at here. So the first x is replaced by x star x, and the rightmost x is replaced by a. Then we have only one x that can be replaced with x plus x, and the rightmost x is replaced by a, and you have only one which can be replaced by a. So if you look at, so what is the yield of the parse tree? You need to read the leaf from the left to right. So leaf nodes, a plus a plus a. So if you collect all the leaf nodes from left to right, that becomes the yield of the tree or the derivation of the tree. So here we have obtained a plus a star e. So can you able to understand what is leftmost derivation and rightmost derivation? So if you choose a leftmost non-terminal to replace by any one of its production rule in order to derive any string, then that is called as leftmost derivation. If you choose a rightmost non-terminal to replace by its any one of the production to derive any string, that is called as rightmost derivation. Clear? Okay, next. So we'll see another example for leftmost and rightmost derivation. Let G be a CFG with production. So there are some production rules are given here. S tends to A tends to small a capital B, B tends to P, B tends to epsilon. So can anyone tell me what are the variables here? Here the variables are S, A, B. That is capital N. Capital N is set of non-terminals. What are non-terminals? Capital S, capital A, capital B. What are terminals here? A and B. We should not include epsilon to the terminal. Okay, so epsilon is a null string. So T may contain A comma B. And there are 4 production rules given. And what is the start symbol? So S is the start symbol. So here you are supposed to derive a string AB. They're using the production rules given. So always you have to start with the capital S. Always you need to start with the capital S. So S derives AA. So you have only one option, isn't it? AA. So look at here. There are 2 non-terminals. You are supposed to choose the leftmost non-terminal. The leftmost non-terminal is A, that can be replaced by its production roots AB. Okay. Then here you have 2 non-terminals, B and A. The leftmost non-terminal is B. So here the B is replaced with epsilon. The B is replaced with B. And you have only one non-terminal capital A, which can be replaced with AB, and then the B is replaced with B. So at last we can able to get AB. Clear? So then we'll move to the rightmost derivation. So always start with the S. S has the production rule AA. So S is replaced with AA. Then you need to choose the rightmost non-terminal. So rightmost A is chosen to replace it as AB. Again, here you have 2 non-terminals. You need to choose the rightmost. So rightmost is B. So that B is replaced with B. Again, you have only one non-terminal A. That is replaced with AB. Then you have obtained. So then this B, you have only one non-terminal B. That B is replaced with B. So the string required is AB, but there are 2 different approaches we have followed to derive AAB. So one is the leftmost derivation, another is the rightmost derivation. So remember, for the leftmost derivation, always you have to choose the leftmost non-terminal to replace it. The rightmost derivation, always you have to choose the rightmost non-terminal to replace by its any one of the production rules. Clear? Okay. So here another example. So if context-free grammar has a production, so here you have 2 non-terminals S and A, and there are production rules given for that. S tends to AAS or A tends to SBA or SS or BA. So show that S derives AA, and the construct a parse tree whose yield is the same string which we have generated, AA. Okay, always you know that you have to start from S. So suppose you are following. So here they didn't mention the approach to be followed. So you may use the leftmost derivation or rightmost derivation. Suppose you are using leftmost derivation. So always you need to start with the start symbol. So S derives A, yes. So there are 2 options, AAS or A. So if you replace this S by A, you cannot expand it further. So what you can take the recursive procedure AAS. Okay. So here you can see there are 2 non-terminals, capital A and capital S. So here, suppose you are going to take, you are going to follow a leftmost derivation, then you need to take the leftmost non-terminal, which is A. So this A can be replaced by its any of the production rule. So here we are going to choose this SBA. So what is the reason? So we know that we are going to generate the string AA. You may have some other option also, but suppose you are trying with SBA. Then what you can do? So in the second step, you can able to identify that there are 3 non-terminals, but you have chosen leftmost derivation. So if it is a leftmost derivation, the leftmost S has to be chosen to replace by its any of the production rules. So here this S is replaced by A. Next you have 2 more non-terminals, A and S. So you need to choose any one of the production rule to replace this A. So here BA is taken to replace this A. At last, there is only one S that can be replaced by A, so that the required string AA, BB, AA is obtained from the start symbol, derived from the start symbol. Okay. So he yield. See, you need to derive the string and you need to construct a derivation tree. So convert this leftmost derivation to a tree where S is the root and this S is replaced by AAS and this A is replaced by SBA and this S is replaced by A and this A is replaced by A, what is this? BA. At last, the last S is replaced by A. So if you read the leaf nodes from left to right, you can get AA, BB, AA, which is nothing but the yield. Okay, yield of the parse tree. So always you have to read from left to right. Clear? Okay. The next one. Consider the following grammar. S tends to BB, AA, A tends to B or BS or AAA. B tends to B, BS, BBB. So you need to find out the leftmost and rightmost derivation for the string. Okay, ABB, BA. And also you need to draw the derivation tree. See, first the leftmost derivation. So you know that always you have to start with the start symbol S. And this S can be replaced by BB. Then you have only one non-terminal B, which can be replaced by BBB. So now there are two non-terminals, but now we are going to use leftmost derivation. So choose the leftmost B and replace it as A. Then you have only ones that can be replaced by AS. Then this S has to be replaced by BB. Then this B is replaced by AS. Then this S is replaced with the BB. At last, this B is replaced with A, the corresponding derivation tree. So S, BB, then this B, BBB, then the left B is by A, and then this B is replaced by AS, then this S is replaced by B, then the B is replaced by AS, then S is replaced with BB, at last B is replaced by A. So what is the yield of the tree? Yield of the tree is BBAA, BBBA. So look at here, BBAA, BA, BA. So the next is rightmost derivation. So you always will be starting with the start symbol S. So S derives BB, then this B can be replaced with BBB, and the rightmost B is replaced with AS, and then this S is replaced with BB, and this B is replaced with AS, and this S is replaced with BB, and this B is replaced with A. At last, this B is replaced with A. So that the corresponding tree, so S tends to BB, B is replaced with BBB, but here what you'll be doing, you'll be replacing the rightmost B as AS and then SS. So it goes like that. So here what is the yield? You need to read from left to right. You need to read the terminals from left to right. BB, AA, BA, BA. So the string is derived in two different ways, leftmost derivation and the rightmost derivation. Next is left and right recursive grammars. So in a context-free grammar G, if there is a production in the form x tends to XA, where x is the non-terminal and A is a string of terminals. It is called left recursion production. The grammar having the left recursion production is called left recursive grammar A. If there is a left recursion production in the grammar, then the grammar is called as left recursive grammar. So which form is called the left recursive production? See, the left hand side of the production, that is always in the left hand side of the production rule, you'll be having one non-terminal. The same non-terminal is present in the right hand, the start symbol of the right hand side of the production. Then the production is called left recursive production. If the grammar contains a left recursive production, then the grammar is called left recursive grammar. Clear? And if in a context-free grammar G, if there is a production is in the form of X tends to AX, where X is a non-terminal and A is strings of terminals, it is called right recursive production. So the right hand side of the production, the rightmost symbol and the left hand side of the production are seen. Then that production is right recursive production. If the grammar contains right recursive production, then the grammar is right recursive grammar. Okay. Then the very important ambiguity in CFG. So when you say the CFG is ambiguous, see, if a context-free grammar G has more than one derivation tree for some string W belongs to L of G with the language generated by the grammar, it is called ambiguous grammar. If there exists a more than one derivation tree or a for tree for any string which belongs to a language which are generated by the same grammar G, then the grammar is said to be ambiguous grammar. We'll say one example for that. So here check whether the grammar G with the production rule x tends to x plus x, x into x, x or a is ambiguous or not. Okay. So in order to check whether it is ambiguous or not, we need to choose a string and we need to check whether there exists two different parse tree for that string. Okay, so we need to check for all the string which are generated. So if there is a string which can produce two different parse tree, then we can conclude that the grammar is ambiguous grammar. So for that, here the string taken is a plus a star a. Okay, so in order to derive that string, there are two different derivations you can take. The first one is x plus a. The first derivation start with the start symbol x and that is replaced with x plus x. Whereas the second derivation x star x. So in both the cases we are applying the leftmost derivation. There is no difference in that. But in order to derive a plus a star a, you may start with x plus a or x star a. So whenever we start with x plus a, then you can replace this x plus x by a, then this x by x into x, then this x by a, then this x by a, at last a plus a star a is subtime. Similarly, in other derivation, you can choose x into x star x, then this x can be replaced with x plus a x, then this x can be replaced with a and this by a and this by a. At last, the yield of the parse tree is same, a plus a star a, but the structure, look at the structure of the tree. So here, both are different. In this level, you have x plus x here x star x. It's not at all a mirror image also, isn't it? So that if there exists two different parse tree for a grammar, then we can conclude the grammar is ambiguous grammar. So this grammar x tends to x plus x, x star x, x or a is the ambiguous grammar because there exists two different parse tree. Okay, then we'll move to simplification of CFG. So how to simplify the CFG? Okay, so there are some methods, some procedures you can follow to simplify the grammar. So in a CFG, it may happen that all the production rules and the symbols are not needed for the derivation of a string. Besides, there may be some null productions and unit productions. So elimination of these productions and symbols is called simplification of CFG. So the simplification essentially compromises the following steps: reduction of CFG, removal of unit production, removal of null production. We'll see one by one. Okay. First, we'll see reduction of CFG. The CFG are reduced in two phases. The phase 1, the derivation of an equivalent grammar G dash from the grammar G such that each variable derives some terminal string. Okay. We can reduce a grammar in two different phases. The first phase, what you are going to do, you are going to fix that if you have a variable that should uh, generate some terminal, it should produce some terminal string. Okay. If not, we can remove that variable. So with that, there are some steps. Step 1, include all symbols W that derive some terminals and initialize I is equal to 1. So include all symbols. So Wi plus 1 that derives Wi. Increment I and repeat step 2. So we are going to check uh, whether a non-terminal we have taken can able to derive a string or not. Okay. Include all production rules that have Wi in it. Okay. And the phase 2, what you are going to confirm, derivation of an equivalent grammar G dash from G such that each symbol appears in the sentential form. See, the first one, it should generate some string. And the second one is it should be reachable from the start symbol. So the sentential form, can you remember the sentential form? It is a partial derivation tree which has a root as a start node. So sentential form, it should start from the start node. So for that, there are three steps you need to follow. Include the start symbol in y1 and initialize I is equal to 1. Include all symbols yi plus 1 that can be derived from yi, and include all the productions that can be applied. Increment I and repeat the step 2 until yi plus 1 is equal to yi. See, in step that is in phase 1, what you are checking whether all the non-terminals are uh, generating or capable of generating terminal string. And the second phase, what you are checking, all the symbols are reachable from the start state. Okay. So if you confirm these two things, then you can generate a grammar or a CRG which is of the reduction. You can eliminate all other non-terminals. Okay, we'll see one example. So find a reduced grammar equivalent to the grammar G having the production rules. Okay, so here the set of production rules are given. S tends to AC or B, A tends to small a, C tends to small c or BC, E tends to AE or FC. E, for example, E. So what are the terminals used in this grammar? Small a, small c, small e are the terminals. Okay. So W1. See, you need to take the A, C, E. See, from the rules, A tends to A, C tends to C, E tends to AE. See, for example, you are taking a set of non-terminals which can able to derive a string. You know that you have a production A tends to small a. So A can generate a small a. C can generate small c. Similarly, this E can generate small e. So, or else if you take this AA also, you can replace this capital A by A. So all these three produces what? A string. Okay, then W2. So we are going to check with this yes. Yes. Since this A and C are the term can able to generate terminals, this AC can also generate. So you cannot. So now you can able to understand all the non-terminal generates a string. Okay. What about the next phase? Okay, that we'll see in the next slide. It's in the phase 2. So S is the start symbol. So y1 is a yes. Then y has a two non-terminals a and c. Since the production rule s tends to ac, and then using this a and c, you can include this a and c. Using the production rule, a tends to a and c tends to c. Okay. Apart from that, we cannot add any production rules because you cannot further increment these things. So the only useful variables and terminals are ACC, AC. So in the given grammar, you can see how many productions: 1, 2, 3, 4, 5, 6, 7. But after the reduction, how many symbols you are how many productions you are having? 3 productions, because all other things are not reachable from S. Okay, clear? And the next is removal of unit production. So, what is called as unit production? Any production rule in the form capital A tends to capital B, that is, a non-terminal tends to a non-terminal, where this A comma B belongs to non-terminal is called unit production. Okay. So, how to eliminate or how to remove the unit production? So, removal procedure. There are 3 steps. Steps 1. To remove A tends to B and the production A tends to X to the grammar rule whenever B tends to X occurs in the grammar. So to remove A tends to B, we need to add the production A tends to X to the grammar rule. Suppose if you have B tends to X. So here X belongs to terminal and the X can be null also. Then what you are supposed to do? You need to delete this A tends to B from the grammar. Repeat the step 1 till all unit productions are removed. We'll see one example for that, then you can understand. Remove unit production from the following grammar. Look at it. There are some production rules here. X tends to AX, X tends to small a, Y tends to Z or B, Y tends to M tends to N tends to A. First of all, identify the unit production. So Y tends to Z is the unit production, Z tends to M is the unit production, M tends to N is the unit production, but not this X tends to A or this N tends to A. What is the reason? A non-terminal tends to another non-terminal is called as unit production, isn't it? See, any production rule in the form A tends to B, where A, B belongs to non-terminal. So taking that into consideration, you can understand Y tends to Z, Z tends to M tends to N are the unit production. So there are 3 unit production in the grammar. As I said, Y tends to Z, Z tends to M, and M tends to N. At first, we'll remove M tends to N because you can see that N tends to A is given. So what you can write, you can remove this M tends to N. Instead of that, what you can write M tends to A. Okay. As N tends to A, we add M tends to A and M tends to N is removed. Okay, the production becomes. So you will be removing this M tends to N and we will be writing the all other things. Now what you are supposed to do? We can reduce this Z tends to M. So here we know that M tends to A. So you can remove this Z tends to M and you can introduce Z tends to small a. Okay. So here the resultant grammar is S tends to XY, X tends to A, Y tends to Z, or B, Z tends to A, M tends to A, N tends to A. So still there exists one unit production, that is Y tends to Z. Okay, now we are supposed to remove this Y tends to Z. So as Z tends to A, we can add this Y tends to A and we can remove this Y tends to Z, so that the resultant production rules are S tends to XY, X tends to A, Y tends to A or B, Z tends to A, M tends to A, N tends to A. But here we can know that M, Z, N are not reachable. So we have seen the first step, reduction of CFG. See here, we can understand that yes, from S we cannot able to reach this Z, M, N. So these are all not reachable symbols or not reachable variables. So we can remove those not reachable variables with its production rules. So the unit productions becomes S tends to XY, X tends to A, Y tends to ERB. So here we have performed two operations. One is we eliminated all the unit production and we have tried to minimize the grammar. So here we have obtained reduced grammar. And the last step we are going to discuss is removal of null productions. So in a CFG, a non-terminal symbol, okay, a non-terminal symbol A is nullable variable. So if you, when can you say a variable as a nullable variable? If it can able to produce a null string or its derivation produces a null string, then you can say the variable as a null variable. Okay. So in a CFG, a non-terminal symbol A is a nullable variable if there is a production A tends to epsilon or there is a derivation that starts with the A and finally ends up with the epsilon. Then you can call that variable as a nullable variable. We have to identify the nullable variable first, then we can remove the null production. So for that there are 3 steps given. Step 1. Find out nullable variables. Okay. Then for each production A tends to A, construct all production A tends to X where X is obtained from A by removing one or multiple non-terminals from the step 1. Step 3. We need to combine the original production with the result of step 2 and remove the null productions. Okay. So we'll see with the example. So remove null production from the following grammar. So S tends to A, S, A, B, B. A tends to B, B tends to epsilon. See, straight away you can see that B tends to epsilon is given. So this B is nullable variable. Similarly, A tends to B is given. So you can replace this B by epsilon. So A becomes nullable. Okay, there are two nullable variables. What are they? A and B. So at first we will remove B tends to epsilon. So after removing B tends to epsilon, the production set becomes. So if you remove this, B tends to epsilon goes, in the sense you will be getting S tends to ASA, AB, BA, or A tends to B, RB, or epsilon, isn't it? So how can you get this? So this B, instead of this B, you may have B or BC, isn't it? Okay. Next, what you're supposed to do, you need to remove this A tends to epsilon. After removing this A tends to epsilon, you'll be having S tends to ASA, AB, B or A. So all those things. So at last you need to remove the unit production also. Because there are 3 steps you need to perform. One is reduction, another is removal of unit production, another is removal of epsilon productions. So if you do these 3 steps, then the grammar becomes simplified grammar. Okay, can you able to understand? Okay, again we'll revise the entire topics once. So today we have discussed about context-free grammars. Okay, so you know that grammar is a set of rules which check whether the string belongs to a particular language or not. Then we have seen this context-free grammar, and this context-free grammar contains 4 tuples n, t, ts, where n is set of non-terminals, t is set of terminals, p is set of production rows, and s is the start symbol. Okay. And we know that the production rule should be of the form n tends to n union d the whole star. That is, uh, in the left hand side you should have only one non-terminal, and right hand side you may have a combinations of terminals and non-terminals, which is of any length. The star meaning 0 or more, isn't it? And we have seen some examples for that. Then we have learned about derivation tree or the parse tree. So derivation tree is an ordered router tree that graphically represents the semantic information a string derived from a context-free grammar. Um, for the derivation tree representation, we should follow this taxonomy. Always the root node should be labeled with the start symbol, and the vertices are the labeled as a non-terminal symbols, and the leaf nodes must be labeled with the terminal symbols or sometimes epsilon also. And we have seen an example for the derivation tree. Suppose if you have a production rule s tends to x1, x2 and so on xn, then the x becomes a root and all other x1, x2 are the leaf nodes from the root s. And we know that there are two different approaches for the derivation tree, top down and the bottom up. In the top down, we'll be starting with the start node, and the bottom up will be starting with the a string and will be ending up with the start node. And we have seen the derivation or the yield of the tree, which is nothing but the final string obtained by concatenating the labels of the leaves of the tree from left to right, ignoring the nulls. And we have seen some examples for the derivation. And we have learned sentential form and the partial derivation tree. A partial derivation tree is a subtree of the derivation tree such that either all of its children are in the subtree or none of them are in the subtree. And we know that if the partial tree contains the start node, yes, then the tree is called the sentential form. So there are two types of derivation tree, leftmost derivation and the rightmost derivation. So when will you call it as a leftmost derivation? Whenever you choose a leftmost non-terminal to replace by its any one of the production rule to generate any string, then the derivation is called leftmost derivation. So rightmost derivation is obtained by applying the productions to the rightmost variable in each step. So we have seen some examples for leftmost derivation, rightmost derivation, and the derivation tree for that also. Okay, then there are two different recursive grammars, left recursive grammar and right recursive grammar. So when you call a grammar G as a left recursive grammar, if there is a production rule is of the form x tends to xa, where x is a non-terminal and a is a strings of terminals, it is called left recursive production. So the grammar having left recursive production is, then the grammar is called left recursive grammar. And if in a context of the grammar G, if there is a production is in the form of x tends to ax, where x is a non-terminal and a is a string of terminals, it is called right recursive production. The grammar having the right recursive production is called right recursive grammar. And then the very important ambiguity in the context-free grammar. If a context-free grammar has more than one derivation tree for some string w belongs to L of G, it is called ambiguous grammar. There exist multiple rightmost and or leftmost derivation for some string generated from the grammar. Okay, and we have seen an example for ambiguous grammar. See here, you can able to draw two different parse tree for a string a plus a star a from the given grammar. So the grammar is ambiguous so that you can generate two different parse tree to derive the same string w. Then we have seen the simplifications of CFG. There are three steps: reduction of CFG, removal of unit production, removal of null production. So first we have discussed about reduction of CFG. So CFG are reduced in two different phases. The first phase you will be checking whether whether the given non-terminal is a generating symbol or not. Generating in the sense it can able to derive any set of strings or not, including epsilon. In the second phase, we'll be checking whether it is reachable from the start symbol or not. Whether it is reachable from the start symbol or not. Okay. So by checking these two things, one is generating and then another is reachable. You can conclude whether the symbol is useful symbol or useless symbol. Suppose if you are finding the symbol as useless symbol, you can remove the useless symbol along with this production rules. And we have seen example for that. So where there are 7 production rules, we have started with 7 production rule and we have ended with only 3 production rules are as a meaningful or useful symbols. All other things are useless symbols. And the removal of unit production. For that, first you have to know what do you mean by unit production. Any production rule is of the form A tends to A tends to B. That is, a terminal tends to another non-terminal, where A comma B belongs to non-terminal. So here there are 3 steps followed to remove the unit production. First, to remove this A tends to B, you need to add A tends to X to the grammar rule where suppose if you are having B tends to EX occurs in the grammar. Okay. And then what you can do, you can delete this A tends to B. And we can repeat the step 1 and 2 until there is no more unit production in the grammar. And the last step is removal of null production. For that, you have to know what is null production. In a context-free grammar, a non-terminal symbol X is nullable variable if there is a production A tends to epsilon or there is a derivation that starts at A and finally ends up with A, that is epsilon. So there are 3 steps to remove the null production. So step 1, find out nullable non-terminal variables which derives epsilon. Step 2, for each production A tends to A, construct all productions A tends to X where X is obtained from A by removing one or multiple non-terminals from the step 1. In step 3, we can combine the original production with the result of step 2 and we can remove the epsilon production. And we have seen one example, remove the null production. So first, by direct, you can see B tends to epsilon is there, so which is B is nullable, you can remove it. From the derivation pattern, A tends to B is given in the production rule so that this A can also derive epsilon. So there are 2 nullable variables, A and B. So at first we have to remove this B tends to epsilon. For that, what you are supposed to do, you can remove as such, but you can substitute this B. Wherever you have this B, you need to substitute its production rules. So this A becomes B comma epsilon. Okay, so that what you can able to do in the next time you are supposed to remove A tends to epsilon. Okay, can you able to understand? So the very important thing, the context-free grammars. So context-free grammar is a way of describing language by the recursive rule or the substitution rules called the production rules. There are 4 tuples used to represent the context-free grammar, NTPS, or we can also say VTPS, variable terminals, production rules, and the start symbols. So here, always the production rule is of the form A tends to alpha. So alpha is nothing but the strings of the symbols from the variables and the terminals. Can you able to understand? So we have seen CFG derivation and its language, very important. So context free language. So if the language L is the language of some context free grammar, then the L is called context free language. So very important, context free grammar, context free languages, and the derivations. There are 2 types of derivations, leftmost derivations, rightmost derivations. And there exists the relationship between the derivation and the derivation tree. Yeah, if you are having a derivation, then you can construct a derivation tree. If you can able to construct a derivation, then you can collect the yields of the derivation tree, then you can call it as a derivation or a strings. Okay. And this simplification of CFG is also very important, because the next class we will be learning about the normalization. So where you need to take a grammar, then you need to simplify the grammar by applying all three steps, then you can convert it to a normal forms. So normalize the grammar means we want the grammar in some specific format. So that means there should be a fixed number of terminals or non-terminals in the context-free grammars. Okay, that we'll discuss in the upcoming classes. Any doubt? Okay, students. Thank you.